All right, so tonight we're going to talk about hypothesis testing, both for 1 and 2 sample tests for means. And then in the second half, we're going to be going over effect size and type 1 and type 2 errors. So to start off, what's hypothesis testing? In hypothesis testing, you have both a null hypothesis and an alternative hypothesis. The null hypothesis is basically the opposite of what you're trying to test. It's basically saying there's no difference or there's no effect there. And then the alternative hypothesis is usually what you're trying to test for. So it's saying there is an effect or there is a difference. So to give an example how to come up with these two, is there a difference in average productivity for a 4-day work week versus a 5-day work week? So one way we could write this is that the average productivity for a 5-day week minus the productivity for a 4-day week is equal to 0. Or you could say productivity for 5 days is equal to productivity for 4 days. And then the alternative hypothesis would be that the 5-day productivity minus the 4-day productivity does not equal 0. So it could be more, it could be less. You could also say that the 5-day productivity is not equal to the 4-day productivity. So how do we test these hypotheses? We use p-values, which are basically probabilities of observing test statistics. So to go back to an example from last week, we had this question here. The average number of scoops of ice cream sold by employees at Scoops Ahoy is 15 per hour with a standard deviation of 3. Steve worked for 6 hours and averaged 18 scoops sold per hour. So if we wanted to calculate the z-test statistic for this, again, here's a reminder of the formula. And here's the problem again. So the population mean is 15. The population standard deviation is 3. The sample mean is 18. And the sample size is 6. So with that, we can do a calculation here. Just import a couple libraries first. And then we can plug in our values. So x bar is 18, mu is 15, sigma is 3, n is 6. And then we just plug that into the z-statistic formula, and we'll print out the z value here, 2.449. So now if we were to plot that on a standard normal distribution curve, we'd get something like this. And then you'll notice I shaded in the area to the right of where Steve is. So that area there is actually our p-value. So normally when we do the cumulative distribution function, if we give it that z-value, it would give us all the area to the left of it. But since we know that the total area under the curve is 1, if we wanted to find the area of just that tail, we can take 1 minus the CDF for that value. So we can do that here, just 1 minus the CDF of a normal distribution at that z-value. And that gives us a p-value of 0.007. So what that p-value says, one way to think about it, is that if we picked a random employee and observed their performance for 6 hours, the same as Steve, there's only a 0.7% chance that they would sell more scoops on average than Steve. So if you think about it, since there's not very much area to the right of it, the probability of observing a value higher than it is very low. So statistically, Steve is pretty good at his job. So choosing the appropriate hypothesis test. This is a flowchart of a bunch of different hypothesis tests. This might look a little daunting at first, but we'll kind of break it down here. So tonight, we're only really going to be concerned with these tests here. 1 sample Z and T test and 2 sample tests. The curriculum also goes over paired t-tests, which we could cover in like a bonus lesson here. Paired t-test is basically if your individuals are staying the same. So if you wanted to measure like patience or something over time at 2 different moments, then that would be an example of a paired t-test. Wednesday, we're going to be going over one-way ANOVA and two-way ANOVA. And then all the ones in the red blocks are non-parametric tests for when you don't have normally distributed data. Those aren't covered so much in the curriculum, but I think we are going to do kind of a big non-parametric lesson here later in the program, just to give you experience with that, because in real life, most data is not normally distributed. So being able to do those non-parametric tests is super important.
I have a question.
Sure.
Yeah, so based on central limit theorem, even though the distribution is not normally distributed, the sample mean, like distribution of sample means, will be normally distributed, right?
Mm-hmm.
So like, can non-parametric test be transformed to a parametric test using sample mean distributions?
I'm not too
Right.
sure actually. I've seen non-parametric also used for when you have like really low sample sizes too, because usually for the parametric test you want like n greater than 30. And I think there are ways to kind of do like transformations on the data to make it approach a normal distribution, if that's kind of what you're saying. But I might have to come up with some examples for you for when we would use those tests in particular.
Okay. Yeah, because at work, I will be dealing with non-parametric tests, so appreciate if actual resources can be shared.
Yep.
Yeah, as a scientist, your question makes me itch, Bonnie. because whenever you change the data like that, whenever you're applying the wrong type of test to the type of sample that you've collected, it changes the reliability of the result that you get out.
Right. Yeah.
Yeah, there's different types of sampling methods to like create normally distributed data. Yeah, I don't think it's so much like let's alter it, but I definitely agree, like anytime we mess with data, we should track what we're doing. Taking a sampling distribution is more like we quit talking about the samples that we have and now we're just talking about the mean, right? Because like when you're taking a sampling distribution, you're typically calculating
That's
the
true.
mean. So it's more like the distribution of this mean versus the distribution of these means. And you're just kind of comparing them that way. That's a good question though, and you can make normal data, or you can do some kind of sampling to like get that in there. But yeah, it's not an issue. You just got to make sure you're talking about the right thing when you're doing it.
Right. Thanks.
But yeah, so we'll definitely do a night just covering those tests then in particular. Okay, so let's take a look at an example problem here. So the average annual earnings for an esports athlete is $45,000 with a standard deviation of $25,000. A recent study of 15 esport athletes found that their average earnings to be $55,000. A rising esports star is trying to decide whether or not to drop out of college and pursue an esports career. His decision will be swayed over whether or not he could expect to make more than $45,000 a year. So we have to design a hypothesis test to test this with a confidence level of 95%. So we can create our null hypothesis first, that the average salary is indeed just $45,000. And then we can come up with the alternative hypothesis that the average salary is greater than $45,000. So we can first create our alpha here. So alpha is basically 1 minus whatever confidence level you want to be at. So if we want to be at 95% confidence, we have to take 1 minus 0.95, and we would get an alpha of 0.05. That 0.05 is like the most commonly used alpha value, but you will see it sometimes less or more. And then we can plug in our data here to calculate our Z statistics. So we have our population mean here, 45,000, our sample mean, 55,000, our population standard deviation, and the number of samples. And if we run that, we get our Z statistic here, 1.549. And then we can find the p-value for that by just taking 1 minus the CDF at that Z value. And we get 0.0606. So if we subtract that from our alpha, we can see it's negative. So our p-value is greater than our alpha. So what that means, since our p-value is greater than that alpha that we chose, we have to say that we fail to reject the null hypothesis. So from this, we can say that despite this new study showing a higher average salary, the average salary of esports athletes is unlikely to be greater than 45,000. So now for a 2-sample t-test, we have 2 games here, League of Legends and Dota. They're kind of similar games, but they have different player bases. And basically, the 2 player bases fight over, which one's superior. So they ran a study to see basically which player base is smarter. So they took 55 League of Legends players and 45 Dota 2 players and found their average IQs, 116 for League of Legends with a standard deviation of 10, and 112 for Dota 2 with a standard deviation of 12. So if we picked a confidence level of 90%, do these studies conclude that one player base is more intelligent than the other? Or in other words, are they equally intelligent? So the null hypothesis is that they are equally intelligent. So the IQ of one is equal to the IQ of the other. And the alternative hypothesis is that they are not equal to each other. So the t-statistic for a 2-sample test is given by this formula here. So the x1 bar minus x2 bar is basically just the sample means, so the difference of those. The mu's here are the population means, which we don't know in this case, but it actually doesn't matter because what we're testing is whether they're the same. No matter what we would plug in here, if both of these values are the same, it would turn out to be 0. So really, this whole numerator here can be thought of as just the difference of the means. All right, and then it's just divided by this down here, the square root of the standard deviation squared, or the variances, divided by the number of samples. So if we plug all this in Python here, we have our alpha of 0.1 because we wanted a 90% confidence. We have the 2 x bars, the sigmas, the n's. The mu's here, I just put in 100 just to show you that it does 0 out. And then since it's a t-test, we need our degrees of freedom, since all the t-distributions are dependent upon the degrees of freedom. And in a 2-sample test, you're going to have possibly 2 different values of n, and you basically take the one that's lower. So in this case, n2 was lower, so we're going to use that to calculate our degrees of freedom. And then this is just plugging in the formula here. There is an easier way to run this. There's a built-in 2-sample t-test, but I wanted you to kind of do it this way first so you can see how the calculations come about. But this gives us a t-value of 1.785. And if we do a CDF with the t-distribution passing in our degrees of freedom and take 1 minus that, that gives us a p-value of 0.0405. But wait, was this question maybe a little bit different than our first one? In the first one, we were only looking at, so here's our normal distribution curve, kinda. We were only wondering if at our z-value, if it was basically greater than, but in this case, we're wondering if it's different than. So it could be greater than, it could be less than. So this means is that there are different types of tests. There's one tail and there's two tail. So in some cases, we could be looking at if the value is greater than, or if it's less than, or we could be looking at if it's just not equal to. In that case, it could be greater, it could be less. So you can see in this first picture, that's kind of like our first problem. We were only concerned with that area there. But in the two-tail test, we have to consider both areas. And since they're equal, since the normal distribution is symmetric, if we find the area of the upper one, we can just multiply it by 2, and then we have the sum of the two areas. So to do that, we just, again, find the t-value, multiply it by 2, and that gives us our two-tail p-value. So this is the correct p-value for testing our hypothesis. And if we subtract that from our alpha here, we can see that our value is less than our alpha. And that allows us to reject the null hypothesis and instead accept our alternative hypothesis. So we can say that based on these studies, the IQ of League of Legends players is statistically higher than the IQ of Dota 2 players. But you can see that if our alpha level was 0.005, then it would have passed on the one-tail test, but it wouldn't have passed on the two-tail test since it's over the 0.05. All right, so here's just a brief rundown of the steps to take in coming up with a hypothesis test and testing it. So you determine the null hypothesis, the alternative hypothesis, and then decide whether it'll be a one or a two-tail test. Then you collect and summarize the data into a test statistic. You use that test statistic to determine the p-value, and then you compare that p-value to the chosen alpha level. If the p-value is less than alpha, then you can say you reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. So we'll hop into an activity now. It's basically 2 questions using some data that's in the repo there. And in each, you basically design a hypothesis and you test it out. So with that, I'll go ahead and pause recording.
Okay, so looking at the problem, we're looking for if professional matches are of a different length than the average League of Legends game. And so what this ends up being is a two-tailed test. So we have 2 sets of data. We have a poll of how long the professional matches are, and then we have this games.csv, which is accepted to be accurate representation of all matches. So that means we can use that as our population statistics. So our null hypothesis ends up being that the average length of professional matches is equal to the average length of the average League of Legends match. And then H1 ends up being that professional matches don't equal the average, the length of average League of Legends game. And so the first thing I did is I imported pandas and set up 2 data frames. One was the one from the general population here, which is the games.csv data. And then the league poll data was league poll df. And I took a look here and saw that we have our game duration column here. Then I set up the problem in order to calculate our z statistic. So we're using a z statistic because we have 1 sample and we know the population. So our alpha is 0.05 because we're looking for it with 95% confidence. Our x bar is the mean of the league poll game length in minutes, and then we multiplied that by 60 to convert it to the same units as the general population statistic. So then our mu ends up being the game duration dot mean from the general data. Our sigma ends up being the standard deviation of that. N is equal to 25 because that's the length of the league poll df. So we actually had 25 data points in there. We set up our z statistic formula here, and we see that we get a z of 1.927. In order to calculate our p-value, we do the 1 minus stats.norm.cdf of z, of the z statistic that we just calculated, and then we multiply that by 2 because it's a two-tailed test. We're not looking if it's greater than or less than, we're looking if it just happens to be different, so it's two-tailed. And we see that our p-value ends up being just slightly larger than our alpha, so we fail to reject the null hypothesis.
All right, good job. Did Bonnie or anyone finish the second question?
Yeah.
All right, do you want to show?
Can you guys see?
Yep.
Cool. So for this one, we are testing 2 different characters in League game. And we want to prove that games with the character Nessus last longer than average than games with Timo, with a confidence level of 95%. So the data in Nessus and Timo will be the sample data. And we are now comparing the sample mean. So this will be a one-tail t-test, because we're testing if Nessus lasts longer than Timo. So the first step is to read the data here. One of them has a count of 28, the other one has a count of 27. So our null hypothesis will be Nessus lasts the same length as Timo. And the null hypothesis, the alternative hypothesis is Timo lasts longer than Nessus. Is that correct? Wait, let me see. Oh, sorry, is Nessus longer than Timo? So be lasts longer than Timo. So maybe I'm wrong here. Wait, I need to change the well, never mind. So the alpha level will be 1 minus 95% and is 0.05, and the x bar 1 is Nessus sample mean, and x bar 2 is Timo sample mean, and sigma 1 is Nessus standard deviation with the degree of freedom equals n minus 1, and the standard deviation of Timo would be the same with the degree of freedom of n minus 1, and the n would be the length, and mu we assume that they are the same, mu being the population mean. And I probably missed out one of the study groups. The t-test, the degree of freedom, is it the lesser, like the smaller n? Matt?
Yeah, so it'll be the lesser of the two sample sizes.
Okay, so I compared N1 and N2, and since N2 is smaller, so the degree of freedom will be N2 minus 1. So here I need to change the formula here, because I assign Nessus to be the x bar 1. So it will be this. And my t is minus 2.458. So now I'm calculating the one-tail p-value, which is p-value, which is, wait.
I think you actually
Is
have
that
the
correct?
characters switched. It should be a positive 2.458, but otherwise it's the right math. You just need to switch those back, I think.
Oh. But I assigned Nessus to be the 1.
Yep, so he should be the 1 because take the Nessus game length minus
So
Timo,
if this
that should be greater than
like,
0.
Am I comparing? Wait, so if p-value is a positive, does it mean that Nessus actually lasts longer than Timo? Right. I'm confused. Wait. What is it? Oh, I did not read it wrong. Sorry, guys. I'm confused myself. So the null hypothesis is correct, and this is the formula is correct. So we have a positive t, which means the p-value is 0.01 and is less than the alpha.
Yep.
So our conclusion will be reject the null hypothesis, and Timo, wait, this is, so Nessus lasts longer, significantly longer than Timo. Okay.
Yep, that's the correct answer. Good job. All right. So with that, we'll pass it off to Raphael here.
Yeah, awesome. Yeah, so this is going to be the effect size notebook that should be in this repo. Let's go ahead and hop on over there. Let me share my screen. All right, so this should be fairly straightforward, pretty quick. But you just learned how to do hypothesis testing, right? And hypothesis testing is great because it can answer this question. If either two means are equal or they're not. And that's well and good. But at the end of the day, we also want to look at effect. Like, how different are they, right? Like, that's really an important question that we want to ask, and that's kind of where we get into effect size and type 1 and type 2 errors as well. So the first thing that I want to talk about is just the objectives. So by the end of this, hopefully you'll be able to differentiate between what distributions look like with high type 1 and type 2 error rates and what they look like with low type 1 and type 2 error rates. Interpret effect size between a set of distributions, and then explain how the effect size affects type 2 or type 1 and type 2 error rates. So what we're going to first do is talk about type 1, type 2. We're going to look at effect size on a distribution. So we're actually going to work through an example. We're going to talk about it, and then you're off on your activity, which is at the bottom of this notebook. I'm just going to import some stuff here, some stuff that we're going to use, NumPy, Pandas, SciPy stats, all that other good stuff. But the big thing is like we have here this type 1 error and this type 2 error. So for the time being, let's just forget about, let's just forget about this real quick. And let's just imagine that we have a distribution like so, and this is kind of where we've set alpha is equal to 0.05. This is what we call a type 1 error. Now, the reason it's called a type 1 error is because let's say we get a data point out here, and this data point comes from our distribution. Well, if it's beyond our confidence level, it's beyond this alpha value, right? It's on this side. We would say it doesn't come from that, right? Like we would say, hey, this is too much of an outlier. There's no way that it came from our H naught population. So we would say this point P does not come from our H naught, right? But we would be wrong because it clearly does, right? It's part of it. We picked it to be part of it, and so therefore we committed a type 1 error. Another way of thinking of a type 1 error is, I believe, I always get this language confused. Let's just look it up. Type 1, type 2 error. And let's just look up the language around hypothesis testing. Yeah, it's false positive. That's great. Here it is. So it's the rejection of a true null. So basically you're saying, hey, I reject this null hypothesis. But like you shouldn't have rejected the null. The null is actually true. And this is what defines type 1 error, is this area. The probability of making a type 1 error is the area under this part of the curve. That's past your critical point right there. So that is type 1. It's just the area under the curve after your critical value. Are there any questions on type 1 error? Okay. So likewise, let's say we're comparing two distributions. Type 2 error is actually the area of your second distribution that comes before this curve, right? In other words, you are, I believe, failing to reject when you shouldn't be failing to reject. Let me see. It is the non-rejection of a false null. So sorry, you're not rejecting a false null hypothesis, and it's dictated by this area under the curve. So just looking at these two pictures, which error is bigger, our type 1 or our type 2 error? Which one do we have a higher chance of committing, or a higher probability?
Type 2.
And why do you say type 2?
Because the area under the curve is bigger.
Yep, that's it. Yeah, it's literally that. That is a perfect answer. Yeah, that is like what dictates this entire thing. Is the probability of you making the error is literally the area under the curve before or after the critical value, depending on kind of which one's which. But yeah, so that brings us to the scenario where we're going to talk about effect size, and you'll kind of like, hopefully through effect size, see the relationship between type 1 and type 2 errors. All right, so our basic scenario is we're testing two groups, POP1 and POP2. I actually changed those names to group 1 and group 2 because they're not populations, they're just groups. Yep. One group is given a dose of caffeine, and the other is given nothing, and then they have to perform deadlifts for max reps. So they just got to go until they can't go. And then we just record the reps, and we run this through a hypothesis test. So if we have two groups, I'm just going to generate some data here. Yep, so here's group 1, and we'll say non-caffeinated. I don't know if I spelled that right. My spelling is not my strong suit, and this is caffeinated. No, that doesn't look right. Caffeinated. All right, so now if we graph them, I'm just gonna plot their histograms and just look at them. And then I'm gonna plot the means as well. So this is plotting the means right here using V-lines. Have y'all seen V-lines before? Yeah, it's awesome. All right, cool. So just looking at these distributions, what can we say about them as far as error goes, type 1 and type 2 error? Just looking at them. Well, anyone? I'll wait. I'll wait a little bit. What looks different about this versus the image we have up here? Because I guess like if we just overlaid these two, you know, it would start it a little bit before 10 and look like that or something. So what's the difference between what we have here and what we have here?
The means are different.
The means are, yeah, those are definitely different. They're different up here as well, right? One's 10, one's like 13. But they're different here. One is 20, what is that, like probably 22 or so. One is 20.
It also looks like they overlap more.
Yeah, there's a lot of overlap. And that's going to be like, and so this is going to show you where hypothesis testing is like kind of limited by itself and kind of how to go for it. So we're going to just conduct a hypothesis test. And our null is that the means are equal. I like to write it out in English right by it just for myself when I go through my notebook. And then the alternative is that they're different. And here we're just going to use stats models to, or sorry, not stats models, SciPy stats. So you can literally just type in stats dot t-test independent. And then we can pass in group 1, group 2. And it'll calculate our critical t-value and our p-value. Now, what do you notice about our p-value?
Very small.
It's basically 0. Right? 10 times 10 to the negative 51st. It's 0, right? So if our p-value is 0, we can reject our null, which means the means are probably different. And you look at this, and they're different because I made them from simulated data with different means, right? This all checks out. But the big question is like, is there an effect? Is there a big, or what is the effect rather that caffeine has on this, on one's ability to perform deadlift reps, right? So that's what we want to answer. Oh yeah, and then we'll we'll get into. We didn't really talk about that unfortunately, but so this is where we talk about effect size, and this is for y'all for later. But for now, I just took this code on how to calculate effect size. And if you look, it's real similar to what you've seen. You take the means of both groups, and then you divide that mean by the square root of the standard deviation of the first group times its population minus 1 squared, and then you do the same thing with the second group. And so you're kind of normalizing it on those standard deviations. And what that tells you is how different these two actually are. You get a Cohen's d of 0.48. So in general, like Cohen's d less than 0.5 is generally a very medium-ish effect. It's kind of small to medium. It's not a really big effect. So for a summary, what I would write is like the mean reps between the groups are different, but the effect is like pretty small, right? It's not like a huge effect. And that's like the benefit of being able to calculate effect size, is because then you can start talking about, all right, well, they're different, but what does that actually mean? Is it something that matters? Is it something that we want to pursue, right? Is this difference something that is something that we should really start to care about? Because just because they're different doesn't mean much, especially in this case where they're like the distributions have such. I mean, if this is our z critical value on our blue population, and it's right here, the probability that we commit a type 1 error is still this area, but the probability that we're committing a type 2 error, and I'll color that in yellow, is like this entire piece. I mean, that's a lot. That's almost the entire distribution of the experimental group. So
what is a normal range of type 2 error?
It can range from anything from 0 to 1. Like it is, you'll see them kind of go anywhere between that. Like, because it's a probability of you saying that you failed to reject the null when you should have rejected the null. So like, for
the smaller the better, right?
The smaller type 2 error, the better. Yes. Yeah. Which is what y'all are gonna talk about, which is good. Like, this is all good. These are great questions. Now here we have effect size for just a single distribution. So like if you have, this is just effect size in general, but like for a 1 sample, let's just say you want to know the effect of maybe some experimental group over a given population or a given mean, right? Like the population mean. You would use this formula where U is the mean of the actual sample distribution that you have. U naught is what you're comparing it to, like the initial population. And then sigma is your standard deviation of the distribution here, with your degree of freedom of 1. I'm only walking you through this because you have to write that code here for that function in your activities, because you need to calculate Cohen's d. 1 sample. So here's the 2 sample. You don't have to do that one. Yeah, I took that from Stack Overflow. It's great. It's a great resource. But for a 1 sample, you need to put this into code over here. All right, so this is the summary that I would write after conducting this test. And now your activity, that's it. That's all I have. I really want y'all to just jump in the activity and start working with this stuff. I went ahead and loaded in your data. And you don't even have to worry about loading it in. So complete the function Cohen D1 sample above. So that's the first thing you need to do. Choose and perform the correct hypothesis test. Choose your test. So in order to do that, the first thing you need to do is ask, is it a 1 sample or is it a 2 sample test? Then you need to write your null and alternative, just like y'all did earlier, just like this. And then after that, you need to calculate the effect size and then just write kind of an overall summary. I would definitely plot them. I would plot the distribution side by side just to see it. It's really helpful to see that. I think I left in a lot of the work for you. Yeah, it looks like I did that. Mostly so y'all could focus on just kind of like what effect size has to do with all this. Because in the first question, I really want you to just kind of walk through a 1 sample. The second one's going to be 2 sample. You can read it. But the big thing, or like at the end, you also have some discussion questions with your group. What changes the effect size between 2 sample population groups? This is a really important question. What changes the effect size? Like, based on what you've done and what you've looked at, what do you know that'll change it? And then ask yourself, if it increases, then your type 1 error rate does what? And if it increases, then what does your type 2 error rate do? So I want you to think about, what does effect size mean and how does it affect our type 1 error rate? Then how does it affect our type 2 error rate? That's your whole assignment, just these 2 questions. Are there any other questions before y'all begin?
So the Cohen's D, I just want to understand the formula. It works in comparing 2 sample mean, and it works in like comparing sample mean with population mean.
Yeah, so there's 2 formulas. One is if you just have a mean and like some data, and the other one's if you have 2 sets of data, right? It's like one you would use if you're doing a 1 sample t-test, one you would use if you're doing a 2 sample t-test. And the 2 sample is usually the one that they actually show online. But it is, I'm trying to find it. I mean, it's essentially this. It's the difference of the means divided by their, what's called the pooled standard deviation. And that is all of this down here, basically, this big formula. Is like it's called the pooled standard deviation formula. You don't have to like be able to interpret this pretty detailed, but just know that it's difference in means over the pooled standard deviation. So
I think that's quite important.
yeah, I mean, it depends on how deep you want to dig into it. It's just it's a type of average, basically, right? You're taking one standard deviation, adding it to another, and then taking the square root of it. So it is like a type of norm average that is used in math.
But in the formula, in the notebook, yeah,
that's right. I'm listening. Go ahead. Yeah, it's kind of like that. That's like one way of writing it. The way that they have here is more like this. Over here. S1 squared plus S2 squared over 2.
So your formula in the notebook, that will be the 1 sample t-test formula, right? And if you want to do a 2 sample, we need to do pooled standard deviation.
Yeah.
Got
yeah.
it.
The 1 sample is just this right here.
Okay.
It's much more simple. But that's it. Any questions or anything before y'all begin? All right. Well, I'm gonna quit sharing. I'm gonna let Matt break y'all into groups, and then we will hop around and
Okay, so the first thing that we kind of discussed was how everything was set up. And what we got was, first off, the two things that we're comparing are the control mean and a group that's a subset of a population. And so here's our hypothesis testing that we set up. For our null hypothesis, we said that the control was going to be equal to the experimental group, meaning the initial recording of typing speed at this company had, they had a certain typing speed, and then the experimental group is where they asked their employees to practice typing for 30 minutes a day. And if the control group, or if the experimental group was different from the control group, then they would get a raise. So the first thing that we did was said that we wanted to do a one sample two-tailed test, because the one sample is because we only have one sample that we're working with. We have a mean, but it's not a sample, it's not a data set, it's just a mean. And then we wanted to do a two-tailed test. And the reason why is because they wanted to see if the practice caused a difference, which to me is kind of funny, because you would think you would want to give the raise to the people that typed faster, but that's not how the problem was worded. So two-tailed test, which we have here. And our p-value was really tiny, like 0. This is our population with two different means. This is the control mean, this is the population mean. So just visually, you automatically know that the means are different. And then the effect size was 0.53. And do y'all want to see my co-and-d function?
Sure.
It's up here. Okay. So we set it up to where mu is going to be equal to the mean of our population. Our mu naught is passed in, so that takes care of the top. And then our standard deviation of the sample with 1 degree of freedom. And then there's the equation. And so that's the function that we used for the one sample co-and-d. Our effect size was 0.53. And since we rejected the null because the p-value was approximately 0, and the effect size was 0.53, which is larger than 0.5, so the effect is of medium to large impact, meaning the means are actually different from each other, and that difference is actually meaningful. So these typing people should get a raise because their typing speed is different. So yeah, that's question 1.
Yes.
Cool.
All right. Question 2, anyone?
Okay.
Well, we didn't finish it.
You can just show what you got to.
Okay. So we were given the two groups. Wait, everybody could see my screen, right?
Yep.
So we were given the two groups, and so we said that group 1, our null hypothesis was that group 1 would be equal to group 2, and our alternative would be that they're not equal to one another, right? So we did our hypothesis test according to what was shown earlier, and we got a p-value of 0, which we were discussing that we would have to reject the null hypothesis, right? And then because this is 2 samples, or we're getting two things given to us, we could use the Cohen-D 2 sample formula that we had, and this is what we got, but we weren't able to discuss that yet.
Okay.
That's all I got. That's
Yeah, in general, that's a big effect size.
right.
1.7. That's pretty massive. So, you'll learn more about that later when you learn about power and stuff, but that's a big effect size. So. Cool. Yeah, everything looks like what I have, and if what I have is good and correct, then this looks good. So, all right. So I just have some questions that I want us to discuss for about 5 minutes or so before we wrap this up. What changes the effect size between two sample groups? I'll just put that. What changes that effect size between them?
The difference of the mean and the variation.
Okay, and why do you say that?
According to the formula or the chart, like if we look at the second one, they overlap less, and also the two sample means they are more apart from each other.
Okay. Yeah, so if they overlap less, so if two distributions overlap less, what does that say about the effect size?
The effectiveness is bigger.
The effect size is going to get bigger?
Yeah.
Yeah, I would agree with that. If they overlap less, the effect size increases. And you can visually see that. These overlap less. We get an effect size of 1.719 at the very beginning. We calculated the effect here, which is like 0.5 or something. So, yeah, 0.48. All right. So here's a question. If your effect size increases, what happens to your type 1 error rate? Does it increase, decrease, or stay the same?
Decrease.
Okay, why do you say decrease?
Because the more different the alpha is smaller, and if alpha is smaller, the type 1 error is smaller.
Why is alpha smaller?
Sorry, the p-value.
Okay. If the p-value is smaller, how does that affect your effect size? Or your type 1 error?
I think the p-value is the probability of type 1 error happen. So is equal to type 1 error rate. Right?
Well, your p-value just has to be less than alpha, right? Whenever you're doing hypothesis testing. So it doesn't really matter if it gets bigger or smaller. What matters is like, is it less than alpha? So it's hard to say.
Okay.
Yeah. But I mean, let's just draw a distribution. So here's one. Let's just draw another one. Let's draw this line that we saw earlier. Okay. Can someone shade in the type 1 error region? Can someone shade it in using the annotation tool? Yeah, that part. All right, cool. Now let's increase the effect size. So what's going to happen when we increase the effect size with these distributions? What's visually going to take place?
Wouldn't they overlap more?
They overlap less.
Oh,
The means are further apart.
Yeah, so we'll do that. Okay, can we shade in the type 1 error region now?
So it's unchanged, it seems.
Cool. Did it change?
No.
No. So effect size has nothing to do with type 1 error rate. Stays the same. Because type 1 error, I mean, if you think about it, it's all about saying, if I pick something from H0, I'm saying that it's not from H0 when it actually was, right? It's all about H0. So you're not moving anything with your original group, right? It stayed the same. Your alpha stays the same. Everything stays the same. All right. So now if our effect size increases, what about our type 2 error rate? So can someone shade in the type 2 error rate on this first graph I drew up here? The type 2 error rate. Ooh, almost. It's actually everything before this line. So it's like all of this. Okay, if I increase the effect size, what's my error rate over here? My type 2 error rate? Yeah, plus this little sliver right there, right? It's all that. Cool. Has that gone up or down or stayed the same? Clearly it is. Not stayed the same. Anyone? Oh, wait.
I think this is what Bonnie was talking about earlier. Because the mean is different and the effect size is larger, those means are further apart. So the type 2 error rate will decrease as your effect size increases.
Yes. Yeah. Yeah, it definitely decreases. Cool. Which is good, right? Like we want a big effect size because it helps us prevent making errors. It kind of gives us more certainty when we're talking about an outcome. There's a whole lot of benefits to having a big effect size on top of your hypothesis testing. So that's it. Thank y'all for having me. This is awesome. Y'all are hard workers. This is cool. Y'all don't play in this class.
Thank you.
And thanks everyone for staying late tonight. I know it's a little later than usual. But this stuff is super important because this is a huge part of your Mod 3 project, hypothesis testing, effect size. So
Yeah.
definitely focus in on this stuff.
Yep. 100% true.
I do have a quick question. So in the real world, type 1 versus type 2, aren't false negatives more difficult to find and deal with? So isn't that why reducing your type 2 error would be really advantageous?
Not necessarily. I think maybe a false negative in something like medicine might be more difficult.
Yeah, that's my background.
Yeah, so there's other fields, like for instance, I worked in advertising where we're trying to just predict if an ad is going to be interacted with, right? Is someone going to interact with this ad? Most of the time, it's 0. People don't do that, right? They just don't interact with ads. So a false negative in that case is like we predicted someone didn't interact and they did interact. And it's like we want to avoid those because it's like we definitely want to know when someone's going to interact, but I wouldn't say it's like easier or harder to detect. I think it's easier to detect because mostly people just don't touch ads, right? Like, so that's like a weird word, and we'll talk about it later. Yeah,
Okay.
Imbalance stuff there.
Okay, that helps.
Yeah.
All right, any other questions before we go? All right, we'll see you guys Wednesday then.
Thank you.
Bye.
Bye.
Thanks. Bye.
Bye, everyone.
Great to meet y'all.